Hello, is my screen visible?
Yes, sir, it's visible, sir.
Okay. Yeah, so the last class I was talking about the development of element level governing equations. So we talked about, just we took an example of two noded truss element. We also call it as a linear truss element. The linear meaning is that the displacement within the element is linear function of x. Linear truss element. So I'm not going to summarize everything, but then what we actually did is that we took this two noded element. This is the x coordinate, the displacement is u in this direction, and we said that this is the local node 1 and this is the local node 2, and of course it is subjected to uniformly distributed load q, and here we had this q1e, and here the load from the other element is q2e. The displacement at this node is u1 and the displacement at this node is u2. So u1 u2 are the nodal degrees of freedom, and then we had said that the displacement approximation within the element is n1 n2 into u1 and u2, and this we said, no, we have defined all these things, no, h into de, and then similarly we said du by dx is nothing but v into de. So here we said, no, h is nothing but consisting of this n1 and n2, and similarly b was nothing but consisting of derivatives of these shape functions, dn1 by dx and dn2 by dx. So yeah, this is we did, and then we developed the element level governing equations from the integral functional. So finally the element level governing equation we said in this form: ke into de is equal to f external for the element plus f internal for the element. So this is what we did, and where we defined now this ke as integration from 0 to L, the length of the element. So we said that the length of the element is small l. So this was ea, and then we had b transpose into b dx. So this was ke, and f external for the element was defined as integral 0 to L, and then we had this h transpose q dx, and f internal for the element was, so this we have already done, I'm just summarizing, and we had this as minus q1e and q2e, and yeah, so we basically we developed this element level governing equation. And also for the specific case where ea is a constant, I had written this ke as ea by l 1 minus 1 minus 1 1, and for q equal to constant within the element, this load vector was ql by 2 1 1. So that also we had done. So now the next step is assembly. So now, as I have mentioned already, that K is a singular matrix, we cannot, no, this equation cannot be solved for no, the u1 and u2. D is nothing but u1 u2, as you see over here. So this is your de. So we cannot solve this. So we, before we solve for the unknown nodal degrees of freedom, we have to assemble and impose the boundary condition. So the next step in the finite element analysis is assembly. Assembly means we are discretizing a given problem into a number of elements, and then we are assembling all the equations together. So in the assembly, essentially we are doing two things. So assembly is basically based on, number one, imposition of continuity of imposition of continuity of primary variables, that is in this case displacements u1 and u2, primary variables across the elements. So that is one. And the second is we are of course looking at the equilibrium of forces. So the second thing involves is the summation of forces at the nodes. Summation of forces at the nodes. So assembly is essentially based on these two concepts. That is, we impose a continuity. So for to demonstrate this assembly, I am going to take a simpler case. So let us take a truss, the rod under axial load, which is discretized only into say two elements. So this is the total discretization. So this is the global node number 1, 2 and 3. The element numbers are, this is element number 1, this is element number 2, and let us say the length of each element is small l. So as I said, no, these the quantities which I have written inside the circles, they are element numbers. So these are element numbers, and these 1, 2, 3 you see. So this one, this is 2, and this 3. So these are the global node numbers. So one we have no the local node numbers, starting node and in node. So we have given the notation 1 and 2, and these are the global node numbers. And if the total length of the rod is L, so you will see that small l is going to be L by 2. So as I said, when we are doing the assembly, so kind of what we are doing is, let us say at node 2 there are two elements. So now as you see here, element 1 and element 2 are connected at node 2. Of course 1 and 3 there is no connection, but at node 2 there is a connection. So first concept, that is imposition of the continuity of displacement, so that would be at node 2. So essentially what we are going to do is that u2 coming from the first element is equal to u, these are 1 and 2 are the local node numbers here, and these are the element numbers. So this is the continuity of the displacement. So in this notation, when I am writing this, these are the local node numbers, and the superscripts are element numbers. So what I am essentially saying, that u2, that is because no, when we look at this global node number 2, this is the second node of first element. So we are saying that u2 from the first element should be equal to, now this node 2 is the first node of the second element. So that is why this first is coming here, and then the element 2. So these two displacements must be same. So that means because u is a primary variable, it should be continuous across the element. So you will have to make sure that these u values are same. And second thing is the the summation of the forces at node 2, because node 2 is common between element 1 and 2. So we have to have the summation of forces coming from element 1 at node 2 and the forces coming from element 2 at node 2. So global node 2. So this is what we do. So in the assembly process, when we look at this, so if you see here, I know before, right now we are not talking about any boundary condition. So as a whole, we will have three displacement degrees of freedom for the the whole element assembly. That is one displacement at one node, global node one displacement at global node 2, one displacement degree of freedom at global node number 3. So let us call them as u1, u2, u3. So there the no these subscripts are the global node numbers. So if you look at this equations are going to be, of course, no there will be a stiffness matrix. So since there are three degrees of freedom for the entire assembly, I am denoting those by u1, u2, u3. Now in this, this u1, u2 and 3, know what we are writing here, 1, 2, 3. These are the global node numbers. So this will be equal to right hand side. We are going to have two vectors, because you have seen in the element level governing equations there are external load vector and there is an internal load vector. So we will have the contribution from those two. So this is what is going to be the assembled system, assembled equations. So now coming to how do we do this? So we'll have to bring in the contribution of first element. We also have to bring in the contribution of the second element. So for that we talk of what is known as connectivity. So I will come back to this again to complete this system. So first we talk of actually connectivity of elements. So connectivity means basically the global connecting node numbers. Global connecting node number. So this is for each element, this is what we call as connectivity. So the connectivity will be for each element. So let us put the element here, element number. So this is going to be element number, and there are two things: starting node, because now the element is right now a two noded element, so we have starting node and we have end node. So this is basically local node 1, and this is local node 2. So if you look at the element number 1, so when you look at this basically no this discretization, so we have two elements 1 and 2 and the nodes are 1, 2, 3. So first element starting node is global node number 1 and the end node is global node number 2. So the connectivity starting node is global node number 1 and in node is global node number 2. Now when we go for the element number 2, so when you see over here, this element number 2 is its starting node is global node number 2. So connectivity is basically between the global node 2 and in node is global node number 3. So we have here 2 and 3. So this is the connectivity. We call this as a connectivity table. So this is simple for because this element is just a two noded 1D element. So element 1 is starting node is global node number 1, in node is global node number 2, and the element 2 starting node is global node number 2 and the in node is global node number 3. So now when we do the assembly, so we look at this connectivity. So if you look at the element 1, so element 1, we know the of course the structure of the equation. So because we are taking this ea and q constant within the element, so the stiffness is ea by l, 1 minus 1 minus 1 and 1, this we have already derived. And if external for the element is ql by 2, and we had 1 and 1. So this is for element 1. Similarly for element 2 also, because we are taking the element length as same, so ke is going to be ea by l, 1 minus 1 minus 1 and 1, it's a 2 by 2 matrix. And if external for this also q is same, so ql by 2, 1 and 1. So these are the element level governing equations. Now these have to be put into this global system of equations or assembled equations. So in the assembled equation, when you look at, we have to bring in the contribution of the stiffness matrix. So as we see in both first element and second element, this ea by l is common. So let me write that ea by l common here. And then now this is the first row, this is the second row, and similar the first column and second column. Similarly you have first row and the second row. So because the first element is consisting of global nodes 1 and 2, and at each node we have just a single degree of freedom. So the first element, first row will go to the first row of the global system, second row will go to the second row of the global system. Similarly, the first column will go to the first column of the global system, and second column will go to the second column of the global system. So I will write here the first row and first column. So EA by L is already taken common. So this first row and first column will go to the first row and first column of the global system. Then this first row and second column, this element will go to the first row and second column of the global system. So it will go over there. Then when you look at this one, second row first column will go to the second row and first column, and then this one second row second column will go to the second row and second column. So this is the global system. Let me try to change the color. So yeah, I think okay. Let me continue with the same thing. Yeah. So now coming to first, let me do everything for the uh, left hand side. So now coming to the second element. So the second element, as per this connectivity table, no, the starting node is global node number 2 and the end node is global node number 3. So that means that for the second element, first row will go to the global row number 2, and second row would go to the global row number 3, and similarly first column will go to the global column 2, and second column, local second column, the element second column will go to the global column number 3. So that means when I now want to take this element of the second element stiffness matrix, so this is the first row and first column of the second element. It will go to the second row, second column of the global system. So it would be added here. So this will be plus 1 over here. Then when you look at this one, minus 1, which is first row and second column of the second element, this will go to the second row and third column of the global system. So now these are the global columns 1, 2 and 3, and these are the global rows 1, 2 and 3. So it will go to the second row and third column. So it would be added over there. And then when we look at this one, the second row first column, so that means it will go to the second row. No, the second row means second row will go to third row, and first column will go to the second column. So this is the third row and this is the second column, so it will be added here. So that is, this particular element will be no, this term of the stiffness matrix will be added here. Then when you come to this one, which is second row second column, will go to the third row and third column, so it would be added here. So now wherever there is no entries, there you put, because those are actually 0. So these elements would be 0. So there is a addition, as you see, there is a contribution from both the elements at this node. So this is the assembly of actually stiffness matrix. And now if you look at the, similarly, we have to assemble the external load vector. First element is defined between global nodes 1 and 2. So as we have already said, its first row goes to global first row, and its second row goes to global second row. So this would be added in the first row here. So it would be 1 here. And let me take this QL by 2 common, because it is common in both the elements. And then this will be added over here in the no, second row. Then coming to the second element, so the second element, this first row will go to the global row number 2. So it would be added here, because already there is an entry from the first element over there. And then this second row of the second element will go to the third row. So it would be no, added over here. So this is as far as the no, the external load vector is concerned. Then we have also the internal load vector. So the internal load vector we have seen, no, q1 minus q1e and q2e. So first element, it would go to the q1e. No, the here you see the subscript is local node number and superscript is the element number with a minus sign. Its minus is already there. Then q21. So these are the contributions from the first element. Then the second element would be minus q1 2, and then you will have q2 2. So this is the assembled system equation. Now this is we assembled in the sense that we have added the contributions of both the elements. So if you look at the, when we multiply this, so essentially the first equation is the force balance at node number 1, because now these are actually three equations. As you see, no, there are three equations. When you multiply the first row of this matrix with u1 is equal to the first row on the right hand side, that's the first equation. When you multiply the second row of this matrix with u1 u2 u3 and take the second rows on the right hand side, that is the second equation. And similarly, when you multiply the third row with u1 u2 u3 and take the third row on the right hand side, you get the third equation. So each equation is a force balance. So first equation is force balance at node number 1, second equation is force balance at node number 2, and third equation is force balance at node number 3. So this is known as the global system equations. Global system equations. Because no, earlier we derived the element level governing equations. Now this is the global system equations, are global system governing equations. So this is what we get as assembly. So this is very important step and you should understand. And as I have already explained you that no, in the notation this q subscript and superscript both are there. So you would see that here in this qij, if you look at, I is the local node number. So that is local for the basically element. So that is local node number, and j is basically the element number. So once we have now assembled these system equations, so the next step comes is the imposition of boundary condition and then solution, because we have not still no got the solution. So we have to solve these equations. Now which equations we I am referring to, basically these equations. As I said, these are three equations. So we want to solve these equations. So for the solution of these equations, before we can solve, we need to impose a boundary condition. So then next we talk of now the boundary condition. See, in the approximate analytical solution where we were trying to find the solution for the entire domain, so there we were imposing the essential boundary condition in weak form beforehand, and both essential and natural boundary condition before substituting the solution in the governing differential equation. We were trying to satisfy all the boundary condition, but in case of finite element, we are imposing the boundary condition at the end actually. So now we talk of boundary conditions. So boundary conditions will be, now let us take the same problem which we were doing earlier. So now the boundary condition is, let us say the left end is fixed, and this is node 1, this is node 2, global node 1 2 and 3, this is element 1, this is element 2, and for each element the local coordinate system origin is at starting node. So for this also the origin will be starting node, and length of each element is small l, which is equal to capital L by 2, we have already said. And the EA is the stiffness and Q is the load, same in both the elements EA and Q. So now if you look at the boundary conditions, we have if you look at the degrees of freedom, we have u1 over here, at this node we have u2, and at this node we have u3. So since this starting in node 1 is fixed, this is the global node 1, so node 1 is fixed, so basically then u1 has to be equal to 0. And second thing, if you look at the right hand side, at this particular node there is no externally applied load. So basically the there is a force is 0 there. So you can say that force is 0, force is 0 at node 3. So this implies that Q22 will be equal to 0, which is EA into du by dx at node 3. So that is no is actually 0 because there is no externally applied load. So that force is 0 over here. So that's the condition at node 3. But additionally, we also have to look at the balance of internal forces at node number 2 also. So that is the node number 2. We need to look at the force balance. So force balance means what? I have to draw the we need to draw the free body diagram of node number 2. So before I can draw the free body diagram of node number 2, let me again remind you that how we consider the element forces. So element 1, know if you just talk of the forces, so we have distributed force, this q, no this is q, and here we have this q11, and here we have q2, sorry, yeah, q21. And when you look at the element 2, so if you look at the free body diagram of element number 2, so we have a distributed force in that. This is a force per unit length, and here we'll have q12, that is local node number 1 and the element number 2, and this is q22. So this is a free body diagram. So if you look at this global node number 2, so it is the basically end node of element 1 and the starting node of element number 2. So we are trying to draw the free body diagram of node 2. So that means we take a cut section over here, we take a cut section over here, and then draw the free body diagram FBD of node 2, free body diagram of node number 2. So this is just the no node number 2, and the forces will be, so if you look at, because it is exerting force on element 1, so element 1 will exert force in the opposite direction. So whatever is acting on the element opposite of that is going to act over here. So this will be q21, and this side the force would be exerted by element number 2. So this force is on the element from node 2, so the force on node would be opposite of this, so that would be q12 in this direction. Although for the problem at hand there is no external force at node 2, so this is node number 2, but let us say I am finally going to put that 0, but let us say there is a externally applied load p at this particular node. So now if we write the equilibrium equation, that is sum of these forces have to be equal to 0. So this force is in the negative x direction, so if I write summation of forces along x direction equal to 0, I will get minus q21 plus q12 plus p equal to 0. So basically then you can say that essentially, if I take these both terms to the right hand side, one side, so I can say q12 minus q21 is equal to p. So that means the difference of these two internal forces, q12 minus q21, is equal to the externally applied load at that node. So for the present case, because there is no externally applied load at node P, node 2, so P is equal to 0. So for the present case, we will have basically uh, Q12 minus Q21 equal to 0 because P is 0. No, this is because P equal to 0. So now if you let me go back to this equation again, the assembled equation. So if you look at in this equation, the number of unknowns, if you look at, no, before we look at the boundary condition, so the unknowns are u1, u2, u3, and also if you look at the unknowns are, no, this q11, q21, q12, q22. So there are too many unknowns, the equations are only three, so we cannot solve. So therefore no, we go for the boundary condition when we look at, and also the element level stiffness matrix is singular, and also the assembled stiffness matrix before the imposition of boundary condition is also singular, so we cannot solve for u1, u2, u3 in case. Now after the boundary condition, so we have additionally got now this u1 is equal to 0, so this is one additional equation. Then we have this q22 equal to 0, that's the third equation. Know that we can say these three equations, and then u1 equal to 0 is the fourth equation, q22 equal to 0 is the fifth equation, and then we have this q21 minus q12 equal to 0, that is the sixth equation. So once we put q22 equal to 0 and q21 minus q12 equal to 0 and u1 equal to 0, so then the unknowns are basically u2, u3 and this q11. And so these are three unknowns, and we can solve for these three these three equations for these three unknowns. So that is how we solve this problem. So the next step we will look at the solution. So in the solution, as I just explained, if you now after boundary condition, if you look at the unknowns, so u1 is already equal to 0, so that's no longer an unknown. u2 and u3 are unknowns, so u2, u3 are unknowns. q22 is already equal to 0, and q12 minus q21 is also equal to 0, that is also known. So the third unknown is basically q11. So these are basically three unknowns. So out of that, if you look at u2, u3, these are the nodal displacements, that is displacements of the nodes along x direction. So these are nodal displacements, and this q11 is essentially another reaction. You may say no, the problem as a whole, so we are trying to solve the whole problem through the essentially finite element, so we are not bringing in the equilibrium, although this is statically determinate, so you can get the reaction at the left end for the whole rod from the, if you draw the free body diagram of the whole rod and apply sum of forces along x direction equal to 0, you will get that. But no, as per the finite element methodology, we are treating this reaction also as an unknown. So now how do we solve? So we have to solve, we have got these three equations, these three equations, what we have over here, these three equations. So now we want to solve these equations for u2, u3 and q11. So how do we solve? So what we do is first, we solve for the nodal displacements. So nodal displacement means if you look at the first equation, you will have this unknown q11. So we don't want to consider that. But if you look at the second equation, that is now the second row into this is equal to second row on the right hand side, and similarly third row into this is equal to the say third row on the right hand side. So these are the two equations. So first we want to consider the second and third equation to solve for u2 and u3, and then from the first equation we get q11. So that is how the solution is actually done. So for these unknowns, so we say that the first solve equations. So let me number this. So these are three equations. So let me say the whole thing I am saying as equation 1, and it has three parts. So 1 1, and so first solve equations 1 2 and 1 3. So this is equation number, and then subscripts are the sub equation number. So we have this 2 and 3 for u2 and u3. So that's the first thing. Hello, am I audible? Hello, am I audible? I think, hello, am I audible?
Yes, sir. Yes, sir. Audible, sir.
Okay. So what I'm saying is that you take the second and third equation from the assembled system and solve for u2 and u3. And then after this, then you solve for basically q11 from the first equation. Then solve for q11 from equation 1 1. So let's do that. Let's do this first one. So we take the equation 2 and 3. So when you go to the equation 2 and 3, again I am coming to this. So EA by L is anyway common. So you multiply, the second row you will take. So this minus 1 into U1 will be there. U1 is already 0. So that contribution will actually go out. So we will have only the second row, third rows, and similarly, sorry, second row and second column and third column. Because U1 is equal to 0, so these will be eliminated. No, the first column of the global stiffness matrix will be actually eliminated because u1 is equal to 0. So then if I look at the equation 1 2 and 1 3, so I will have this EA by L common, and the second row, second column is 1 plus 1, that is 2, and second row third column is minus 1, then third row second column is minus 1, and third row third column is plus 1, and then these unknown displacements are u2 u3, and on the right hand side you have this ql, and here you have 2 and 1, because 1 plus 1 it is 2, and the plus we have this 0, this 0, these terms are 0. So actually this is what you have. So now you can, as you see, these two equations can be solved for u2 and u3. These are two set of simultaneous equations and can be solved for u2 and u3. So from this, when we solve, you can straight away, I suppose you know how to solve the set of simultaneous equations. So that much you must know. So you can first say from first equation you can either use the elimination. So you can eliminate, or you can use the substitution method, anything you can use and solve this. So u2 will come out as, so if you solve 3ql square upon 2ea, and if you solve u3 will come out as 2ql square upon ea. So this is the solution of these equations, and we already know u1 equal to 0. This is from boundary condition. So yeah, we know this, so from the boundary condition, and then from equation 1 we solve for q11. So now we have already got u1 equal to anywhere 0, u2 u3 we have got, and then we want to take the first equation. So from equation 1 so if you look at the equation 1 so ea by l is common over here. Again I am coming to this equation, so I am taking the first equation. That means this row into this column over here. So u1 is already anyway 0, so we will have this element into u2, and this is already 0, so you will have only that term. The right hand side you will have ql by 2 and minus q11. So that is going to be the first equation. So we basically have minus ea by l into u2 is equal to ql by 2 minus q11. So from this, if you now u2 value is already known, so you can say that q11 would be equal to ql by 2 plus this ea by l into value of u2, which is 3 ql square upon 2 ea. So if you simplify this, comes out as 2 ql, and that is what is the reaction actually. So now if you look at the rod as a whole, so this side, the reaction force is your q11, and the distributed force is the q, and total length we have taken as 2 into small l. So if you write the sum of forces along x direction equal to 0, so you will get q11 is equal to 2ql. That is what is coming from the finite element solution, that we are getting the reaction at the left end as 2ql. So this is what you are getting. So now once we have done this, so then again we would be interested in finding out the displacement within each element, the strain within each element, the stress within each element. So all that is that comes under basically post processing. So the next step is, so now if you have any questions and doubts, please ask. So the next thing is post processing. So now after the element level governing equation, we have done the assembly. After the assembly, we have imposed the boundary condition, and after imposing the boundary condition, we have solved for the unknowns u2, u3 and q11. and after that we want to do the post processing, and this will be done element wise. That means we have to do for each element wise. So now if I look at the element 1, so first we talk of displacement. So we know that u is equal to, we have already done this interpolation, n1 u1 plus n2 u2, and now you know this n1 is basically 1 minus x by l. So the this is the first element, this is the global node 1, global node 2, and the local coordinate system is capital X, length of the element is L. So 1 minus x by L, x by L into u1 and u2. u1 is 0 and u2 is 3ql square upon 2ea. We have already solved for this now. So now this, if you simplify, so the first term is anyway 0, so you simply get 3ql square upon 2ea into x by l. So this is the displacement. If I want to calculate, let's say at the center of the element, what is the displacement, I just put capital X is equal to L by 2, small l by 2, and get the displacement at that node. So now from this you get the displacement at any point within the element. So within the first element you can put this capital X, any value of capital X between 0 to small l, and you get the the displacement within the element. So now the next thing is the strain. So now if you look at the strain is, let us say, epsilon xx. I'm using subscripts as capital X, although you can use small x also. So that is du by dx, and so if you differentiate this, so you will see that this will be simply, this x will go, so you will get an l and l will cancel, so 3ql upon 2ea. That is what would be the strain. And now what we see, because in this element the displacement is linear within the element, so the strain is constant. So throughout the element we are getting the strain as constant, which is 3ql upon 2ea. And if you look at the stress similarly, because for the design you need know the stress, because you will be comparing this with the design stress. So then sigma xx would be equal to E times epsilon xx, and so therefore this would be 3ql upon 2a. This is going to be the stress when you multiply with the strain. So this is the displacement anywhere within the first element, this is the strain, and this is the stress within the first first element. Now if you look at the element number 2, so for element 2 again you will have u is equal to 1 minus x by l, x by l, and now the local node 1 is global node number 2, so I'm writing the first degree of freedom as u2, and this will be actually u3, and this is the now element, this is a capital X coordinate, this is a global node number 2, which is its starting node, and the end node is global node number 3. So this is element number 2, and these are the u2 and u3, and if you put the values, so we have 1 minus x by l and x by l. u2 we have already written as 3ql square upon 2ea, and u3 is 2ql square upon ea. This we have already solved for. So now if you put multiply this with this here and simplify, so finally you will get this as 3ql square upon 2ea plus ql square upon 2ea l into x. So this is what you will get. So again, as I said, using this you can calculate the displacement anywhere within the second element. So if you had to calculate displacement anywhere within the first element, you will use basically this equation, and if you have to calculate the displacement at a location which comes within the second element, then you will use basically this equation. And then the strain similarly for the second element, if you look at the strain, epsilon xx is equal to du by dx. So this will come out as basically, this is a constant term, this is only function of x, so you will get ql square upon 2 ea l, so you can write that as ql upon 2 ea. And stress, if you look at stress, which is sigma xx will be equal to E times epsilon xx. This is no uniaxial state of stress. So other than sigma xx, all the stresses are zero. Sigma yy, sigma zz, tau xy, tau yz, tau zx, they are all zero. So this will be equal to, as you put here, it would be ql upon 2a. So this is what is going to be the stress. And as I already mentioned, sigma yy will be equal to sigma zz equal to tau xy equal to tau yz equal to tau zx. These will be zero. So any axial state of stress. Similarly, the strains, if you look at epsilon yy will be equal to epsilon zz will be equal to minus nu times epsilon xx, and all other shear strains gamma xy, gamma yz, gamma zx, these will be actually zero, because no, this is the uniaxial state of stress. So these all the stresses are zero, only this stress is non-zero. And in the strain, because of Poisson's effect, we will get epsilon yy and epsilon zz, but the shear strains would be zero. So this is what, no, so you have, the post processing. Now before I move further, I want to show you how we compare, the exact solution and this finite element solution. So that's the next thing I want to do. So although you remember, through the approximate analytical solution, we have done the the exact solution of this problem by making the residual equal to zero throughout, but let me do it slightly differently. So that is just to give you an idea that how the finite element solution compares with the exact solution. And of course, this is a simple problem, so for this exact solution exists. But for more complex engineering problems, you see, the analytical solutions do not exist. So we then rely on this and maybe some comparison based on strain gauge measurement and those kind of things. So but for this, at least we will have confidence on finite element method, that yes, no, it gives accurate solution compared to exact solution wherever it exists. So exact solution, if you look at, EA and Q are constant. So the differential equation will become simply EA into dtu by dx square plus Q equal to 0. Now here X is the global coordinate system. Global coordinate. So I'm not using the local coordinate. So global coordinate. So the problem we are taking is that the entire domain as a whole, this end is fixed, this is small x, in this direction displacement is u, and the total length is 2l. No, l small l is the length of each element. So we want to have it in that form so that we can directly compare with the finite element solution. So this is distributed load q, and product of Young's modulus and cross sectional area is ea, and EA and Q are constant along the length. So now you can write this equation as d2u by dx square is equal to minus Q upon EA. So that is straightforward. Now if you do the integration once, you get du by dx is equal to minus qx upon EA. Q upon EA is constant, plus a constant of integration, say c1. And when you integrate once again, you will get this as minus qx square upon 2EA plus c1 into x plus c2. C1 and c2 are the constants of integration. So this is a very simple problem. The exact solution is straightforward. So here c1 and c2 are constants of integration. Constants of integration. And these constants would be determined from the boundary conditions. So if you look at the boundary condition now for the problem as a whole, not for the finite element. So if you look at the boundary condition, one is that u equal to 0 at x equal to 0. So if you put no, here x equal to 0, this term is 0, this term is 0. So this will give you c2 equal to 0. And the second equation is du by dx is equal to 0 at x is equal to 2l, which is capital L. Capital L is equal to 2 into small l. So now from this you will get, basically, if you put here, so we will get minus 2ql upon EA plus C1 equal to 0. So that will give you C1 is equal to 2ql upon EA. So therefore finally you can say the solution u would be minus qx square upon 2EA plus 2QL upon EA into X. So this is the solution. This is the exact solution, and you know the exact solution is quadratic function of X, as you see here. In the finite element, we have linear variation within each element. Of course, for the problem as a whole, that would become bilinear, because two linear curves, one from 0 to L, another from small l to 2 into small l. So, but the exact solution is quadratic, as you see from here. This is the exact solution. Now, if you look at the strain, epsilon xx, so the epsilon xx is going to be du by dx, and this will be equal to minus qx upon ea, as you see from this. You differentiate, so 2 and 2 gets cancelled, and plus we will have 2ql upon ea. So this is going to be the strain. And if you look at the stress, sigma xx e into epsilon xx, so this is going to be basically minus qx upon a plus 2ql upon a. So this is the stress. Now let's know, we want to compare. Now we have got the everything from the analytical solution, also the displacement u, the strain epsilon xx, and the stress sigma x. So these are there as function of small x, which is the global x coordinate. Now we want to compare the values of displacements and stresses and strains at different points. So first let me compare the displacements at node 2 and 3. That is what we have got directly from the finite element solution. So now if I look at at node 2, the finite element node 2. So at node 2, basically we will have small x is equal to this is small l. So if you want to calculate u, u will be equal to u2, and u2 is nothing but value of u at x is equal to small l. So if you put the values, so you will have minus q. No, in this solution you are going to put the values. So minus ql square upon 2ea plus we have 2ql square upon ea. So this comes out as essentially 3ql square upon 2a. And this is what we have got. If you see above, you have got u2 is equal to 3ql square upon 2a. So although in the finite element, within each element we are taking the u as linear function of x, but at the node we have got the value of u which is exactly same as exact solution. So this is the exact solution. And if you see here, u2 is equal to same, we have got no here no this 3ql square upon 2a, so exactly the same thing. And similarly keep in mind this u3 is 2ql square upon a. And let's look at from the exact solution. So now let me see at node 3. So a small x would be equal to 2l, because l plus l. So u3 is nothing but value of x at x is equal to 2l. So if you put the values, so you would find that this will come out small x is equal to 2l, that is what you're putting. So 4ql square upon 2ea plus 4ql square upon ea. So this comes out as 2ql square upon ea. So as you see, this is exactly same as the finite element solution. So finite element solution is matching with the exact solution at node 2 and node 3. Node 2, and this is at node 3. So finite element solution and exact solutions. Of course, this is happening for this particular case. It may not always happen, but when you increase a number of elements, if you keep on increasing for a certain number of elements, which is known as converged mesh, you will match the Phi solution with the exact solution. So as a conclusion, we can say here that no displacements at nodes obtained from finite element solution match with those obtained from exact solution. Of course, the difference you will notice if you calculate somewhere in between the no elements, you will not match there. So no, this is only at the node points. Suppose I calculate the displacement at center of no, first element or center of second element, and calculate the corresponding values from the exact solutions. If I want from the exact solution, that is from this one, if I want the displacement at center of first element, so I will put small x is equal to L by 2, and whatever I will get, that will not match with what we will get from the finite element solution. Similarly, if I take the center of second element, that is put small x is equal to 3 small l by 2, and get the value from here, will not match what we will get from the finite element solution. So this is an observation which I want to highlight. However, within the elements, within the elements, FE solution is linear, linear in X, but exact solution is quadratic. Exact solution is quadratic, quadratic function of small x. So this is about the displacement. Now let's come to the stresses. So now coming to the stresses, now what I will do is I will compare the exact solution and the FE solution. Although in FE solution we have got the stress constant, stress and strain constant within the element. But let me take the center of element. So center of element 1, element 1. So sigma, no, you can use either capital X subscript or small x, that really doesn't matter. So this is sigma xx at x is equal to L by 2. So because no, in the FE solution we have got constant stress, so it is independent of capital X coordinate. So this will be simply 3QL upon 2A, that we have already calculated. So this is the FE solution. And now if I calculate the same thing, sigma xx at no, small x is equal to L by 2 from the exact solution, so you will find this will come out as 3QL upon 2A. What I am saying is that we have got, no, this is the expression for stress from the exact solution. If you put here small x is equal to small l by 2, you will exactly get, no, this expression. So this is the exact solution. But of course at the center of the element. And similarly, if I look at the center of element 2, so I get sigma xx at x is equal to, again for the second element, because a small, no, this capital X is a local coordinate, so it is L by 2, and we have already got this as QL upon 2A. So this is the finite element solution, FE solution, FE solution. And from the exact solution we will get the small x is equal to, we have to put 3L by 2, because that's the center of second element. So will be, this will be also equal to QL upon 2A if you put in the exact solution. That is, if you put here what we have got, if you put here small x is equal to 3L by 2, you will actually get this solution. So this is the exact solution. So again, what is the observation? The observation is that stresses at the center of the element match between the FE and the exact solution. So you see exactly at the center. Uh, I think, yeah, no, I'm sorry. This is the, yeah. So you see that these two results match, and similarly these two results match. So you can say that the stresses at the center, although if you see within each element the stresses are constant in FE solution, whereas in the exact solution they are linear functions of no, basically x, but at the center of the element they actually match. So the observation is that stresses at the centers of the element match with the exact solution. So that is FE stresses, that is stresses obtained from finite element at the centers of the elements match with the exact solution. So now let me plot all these things. So for plotting, what I will do is, first let me look at the displacement. Let me show you how these results FE and exact solution compare. So let me just say displacement plot. So what I am doing is, yeah, this is the displacement along x direction, that is u, and this is your no this direction is your x coordinate. So if you look at the exact solution, of course u is 0 at the center, and in between it is quadratic. So if you plot roughly, that plot would come out something like this. Let me put it more. So that displacement plot would be something like this. This is the exact solution. So it's a quadratic. So as you see, this is a nonlinear curve. So this is the exact solution. That is, I'm just trying to show you this plot of this expression what we have got over here, this one. So now if you uh, plot the finite element, so we have discretized the whole thing into two elements. So one solution is from here to here, and the other solution is from here to here. So these are the FE solution. This is FE solution. This is also FE solution. So you see, at the nodes they match. No, these are the node points. The two solutions match, but in between there is a difference. So it's like, in terms of FE, this is node 1, this is node 2, and this is node 3. So in between there is a difference between FE solution and the exact solution, but at node points they are matching. So if we increase the number of elements, you will find that FE solution would be closer and closer to the exact solution. So, but one more observation from this is that in FE and exact, U is continuous across the elements. So that is, we have the continuity of U. But if you look at du by dx is discontinuous at node 2 from the FE, but it is continuous from the exact solution. So you want one more observation is that in FE and exact solutions, U is continuous no across the continuous across the domain. So particularly at node 2, we get the same value of u whether we come from element 1 or we come from element 2. So that is what during assembly we have imposed this continuity, and therefore we are satisfying this. But if you look at du by dx, is discontinuous at node 2 in FE solution. Now similarly, let me show you the stress plot. So if I look at the how the stress plot is coming from these two solutions. So this is the length, and this side is we are taking sigma xx, and this is the x coordinate. So if you look at the FE solution, we have got the stress here, which is a linear no function of x. So at x equal to 0 it is going to be 2ql by a, and at x is equal to 2l it is going to be actually 0. So that is the plot you will get. So you will see that is going to be something like this. So this is the exact solution, and this value here is 2ql upon a. This is the exact solution. If you look at the FE, So the first element is giving you some result which is constant like this, and the second element is giving you some result like this. So this is basically, you can say, node 1, and this is node 2, and this is node 3. The values, if you look at this, we got as 3ql upon 2a from Fe, and this value we got as basically ql upon, so this was what, ql upon 2a. So this is the Fe solution, and this is also the Fe solution. So you will see the results are only matching at the centers of the element. This is the center of the first element, this is the center of the second element. So this is center of element 1, and if you see, this is center of element 2. So at those places only the values are matching. At all other places there are differences. So this is what, no, and if you look at node 2, I already said there is a discontinuity in du by dx from Fe solution. So and at node 2 you see another thing is that element 1 is giving you the stress as 3ql upon 2a, whereas no, the element 2 is giving you the stress value at the same location, node number 2, as ql upon 2a. So there is a discontinuity, and this is the obviously, u is continuous, is c0 element, so u is continuous, du by dx will be continuous at nodes, but this discontinuity will reduce with increase in the number of elements. So if you keep on increasing the number of elements, you will get the Fe solution closer and closer to the exact solution with no, the discontinuity will keep on reducing. So I can say that here the difference in stresses, no, here big actually no exact, so because there is no concentrated force at center at any point, so the stresses are continuous. Of course, if there are concentrated forces, then there would be discontinuity in the exact solution also, but here Fe, although in exact solution there is no discontinuity, but Fe solution is giving, there is a no, showing the discontinuity. So difference in stresses at common nodes will reduce with increase in the number of elements, with increase in the number of elements. So so that is what no, what I want to say from this, that for the same stress, if I look at, no, if I look at sigma xx over here, and the exact and the Fe solution, so this is exact, as you know, if I have more number of elements, so I will get the stress distribution like this, like this. So you will get like this. So you will see that this difference, the mismatch at the common nodes, this mismatch will actually reduce with the increasing number of elements. So this will be the exact solution, and these are the Fe solution, like staircases Fe solution. This side is X. So this is what we actually expect. Now let me so yeah, this is the, so I know I will not be, of course, going in so much of details when I discuss subsequently different elements, but because this is the first example we are taking, so I have gone into each and every detail about how we solve this problem. So the next is, let me take another example. Now if you want to solve the same problem. Now, before I go to the next example, the same problem, suppose you wanted to solve with this end also is fixed. So suppose if this end is fixed, then you can still discretize this into two elements, and then u1 will be equal to 0, u3 will be equal to 0, and q12 minus q21 will be equal to 0, but then basically q22 will not be equal to 0 because this end you are fixing. So first you will solve the second equation for u2, and then first equation you will solve for q11, and then the third equation you will solve for q22, and then of course you can do the similar thing. So with the same assembled system you can solve basically the different types of problems with different boundary conditions. So now let me take the second example, a slightly different one. So example 2 on the rod itself. So let us say that we have a rod but with variable cross section. So part of it has a cross section 2a. So product of E and A is 2ea, and here it is just the cross sectional area is A. Additionally, it is, let us say, fixed here, and it is fixed here. And now instead of there can be distributed load also, but I am not considering that. Let us say at the center there is a concentrated force P, and there is no Q. So Q is 0 here and Q is 0 here, no distributed force, although it can be there. And let us say the length is small l, and this is also is small l. And so nodes are, let us say we still want to discretize this, because for one part of it the cross sectional area is 2a, and for other part it is a. So we need to discretize this at least into two elements. So one, this element 1, and this is element 2. So the nodes are, let us say this is node 1, global node 2, global node 3. The element is, this is element number 1, this is element number 2. Although you can always discretize this into more number of elements, but I'm just talking about the simple discretization. Just uh, now you will see the element level governing equation form of the element level governing equation is going to be same. So if you look at the element 1, so Ke, the stiffness matrix is only now Ea is replaced by 2Ea, because but it is still constant within the element. So the stiffness matrix would be 2Ea by L, 1 minus 1 minus 1 and 1, and the load vector will be equal to, if you look at the F external for the element, because Q is 0, so that will be 0 0, and the F internal of course for this element would be equal to minus q11 and q21. So this is for the element 1, and if you look at the element 2, so element level stiffness matrix, now for that element 2, Ea is simply Ea, so it would be Ea by L, 1 minus 1 minus 1 1, and F external of course is going to be a null vector, because q is 0, and F internal, if you look at F internal, would be equal to minus q12 and q22. So I'm for q I'm still using the local node numbers and the superscript as the element number. So now once we have this element level governing equations, so we do the assembly. That's the next step, we always do that. So now if you look at the assembly, again no, before looking at the boundary condition, we are discretizing this problem into basically two elements. So there are total three displacement degrees of freedom. So if you look at the equations, the stiffness matrix is going to be of size 3 by 3, three displacements u1, u2 and u3. And the right hand side, because the external load vector is 0, so we will have only the internal load vector coming over here. So we will have basically this. So as you know, now the same concept which we have used earlier. So the first element contribution will go to the first and second rows and columns. So the first one will be 2a Ea by L minus 2 Ea by L minus 2 Ea by L and 2Ea by L. So this is the contribution to the stiffness from the first element. So this is the first column, second column, third column, first column, second row, first row, second row and third row. So the first two rows and columns of first element are going into first two rows and columns of the global stiffness matrix. And then the second element is defined between global nodes 2 and 3. So it will go to the global row number 2, 3 and column number 2 and 3. So we will have plus here EA by L minus EA by L minus EA by L and EA by L 0 0. So the concept is same. And the right hand side we will have minus Q11, we will have Q21 minus Q12, and we will have Q22. So this is the assembled system. Now this boundary conditions, if you now look at the boundary conditions, so the boundary conditions are one, because we are taking, this node is fixed, so u1 has to be equal to 0, u3 has to be equal to 0. So we will have u1 equal to 0. The second boundary condition is u3 equal to 0, and third condition is that we have already, from the equilibrium of node 2, we have already shown that q21 minus q12 is equal to p. So we will have uh, q q21 q21 minus q12, this will be equal to p. So now after these boundary condition, if you look at the unknowns, what are the unknowns? Now u1 and u3 are already 0, so they are known. u2 is an unknown, so that is 1. And this q21 minus q12 is equal to p, so that is also known. So these are additional unknowns, q11 and q22. And now you see this is a statically indeterminate problem, because now you have two reactions at right end and left end, and you will have only one equation of equilibrium force equation, so you cannot find those. But in FE solution, whether it is statically determinate or indeterminate, we handle the problem exactly the same way. We don't have to do anything else. So now you have this q21 minus q12 equal to p. So now if you next step is solution. So if you solve, now since u1 and u3 they are already 0, so first we take the second equation and solve for u2. No, so the second equation, if you see, this term into u1 is going to be 0, and this term into u3 it is going to be 0, so only this into u2 is equal to right hand side, you have basically p. So if you look at the say the second equation, you will have 3ea by l, 2a by l plus a by l, 3a by l into u2 is equal to p. So from this you will get the straight away u2 is equal to pl upon 3ea. And then if you look at the first equation, you can solve for basically no q11. So first equation is this 2a by l into u1, which is 0, minus 2a by l into u2, which we have solved for. So we have minus no, not minus, 2a by l into u1, which is 0, and minus 2a by l into u2 is equal to right hand side, we have minus q11. So you will see we get q11 is equal to 2ea by l into u2, which is 2ea by l into u2 is pl upon 3ea. So you will see that this q11, which is the reaction at left end, comes out as 2p by 3. And then from the third equation, if you look at the third equation, so third equation is similarly, now you have 0 into u1, so that is already 0, and minus a by l into u2, and then a plus ual by u3, u3 is equal to 0, and the right hand side is q22. So you will get from this basically minus a by l into u2 is equal to q22. So you will see that q22 is equal to minus a by l into u2, and u2 is pl upon 3ea. So this will be minus p by 3. So this is the as you see is the reaction forces. Of course, the post processing you can exactly do in a similar manner. So you can calculate the displacement anywhere within the first element, and the same way the displacement within the second element anywhere. Also calculate the strains and stresses. You can do all those calculations. And now if you look at the force equilibrium for this problem, so we have we said here it is actually p. and q11 we got it as 2p by 3. So this is 2p by 3. Q11 direction is this. And if you see q22 direction was in this direction, but it is minus. So if I take that minus, so it would be p by 3 in this direction. So you see that equilibrium of forces, this 2p by 3 and p by 3 is the negative x direction, is equal to p, is balanced by this. So you see that sum of the force sigma fx actually equal to 0. So that means you see equilibrium for whole structure is satisfied. Equilibrium for whole structure is satisfied. Yeah, so I think Anu, I want to stop here, and please go through all these concepts carefully, and if you have any doubts and questions you can ask. You can ask even now also, or if you have any doubts and questions. And so the next class I will be starting a quadratic truss element. So rather than assuming a displacement approximation linear within the element, we take the displacement approximation as quadratic within the element. How we develop the element level governing equations and how we use that for solving problems. So that is what I will be doing in the next class. So now if you have any doubts and questions, yeah, you can ask. So yes, any doubts, questions? Anybody? So these are very basic steps of finite element, and you should understand all these steps. Yeah, so any doubt, question, anybody? Yes? Okay, so if there are no questions and doubts, I'm stopping. Thank you all for your attention.
Thank you, sir.